Alright guys, we're going to practice finding the area under two curves and then the area between two curves. So we'll do 4 examples in this video. So the first one we're going to do is number 2 from the practice problem set. Our function is negative 12x squared times 4x cubed minus 1 cubed. And we're looking from 0 to 1 on the x-axis. So what we're trying to find here, and it's good to get in the habit of writing this as an integral, is from 0 to 1, the area under this curve. Alright, so we're going to need a u substitution here because we do have a composition that's going to work out sort of nicely. So I'm going to let u equal 4x cubed minus 1, and that's going to mean that du is equal to 12x squared, which is great news because that's a component of what we're looking for here. Dx. Okay, and we also need that dx, right? So this is going to allow us to do something sort of nice, but just be careful about this negative, right? We do need to represent that negative, so what I'm going to choose to do here instead is write this as negative du equals negative 12x squared dx. And now I have every component that I'm looking for. I've got the negative 12x squared, I've got the dx, I've got the 4x cubed minus 1. So now I can rewrite this integral as long as I make sure to account for the fact that I'm letting x equal 0, which is going to affect u. So negative 1 now is my new bound, my new lower bound, and then if x equals 1, then u is going to equal 4 times 1 cubed minus 1, which is going to be 3. Alright, so I've got a new integral that I'm solving here. The integral from negative 1 to 3 of u cubed negative du, and I'm going to move that negative outside of the integral. So this is going to allow me to use the reverse power rule, so that's going to be equivalent to negative 1/4 u to the 4th from 3 to negative 1. Alright, now I can plug in my values and subtract. So this will be negative 81/4 minus 1/4, which is negative 80/4 or negative 20. All right, let's do example number 3. So we're trying to find again the area under this curve of this function f of x from e to e squared on the x-axis. So I'm going to rewrite this as an integral first. So from e to e squared, ln of x over x dx. All right, I will use a u substitution here. I'm going to let u equal ln of x. So let u equal ln of x. And that's going to mean that du is equal to 1 over x dx, which is great because that's going to account for this component here, the 1 over x, that's there, and the dx, that's there, so that's good. I've taken care of everything, and I've got my ln of x. So now I can rewrite this as the integral of u times du. But I need my new bounds. So if x is equal to e and u is equal to ln of x, then in this case u is going to have to equal 1. So that's my lower bound. And if x is equal to e squared, u is equal to ln of e squared. What power of e would equal e squared? 2. So a nice integral for us to evaluate here. I'm going to use my reverse power rule. So this is going to be 1/2 u squared evaluated from 2 to 1. So this is going to be equivalent to 4/2. I could write that as 2, but this is 1/2. So we have our common denominator, 3/2. All right, let's talk about examples 4 and 5. So find the exact area between the following curves. These are some examples we're going to want to talk about here. So what you need to do is figure out not just what the area under each of these curves is, but the area in between them. And if I were to sketch these, not that I expect everyone to just immediately know what these would look like, but if you think about them for a second and you think about what you know about them, this is a linear function with a negative slope and a positive y-intercept. So just off to the side here, I'm just going to picture what's going on. It's a y-intercept of 3, and we've got a negative slope. So something like that going on, right? A negative slope of 1. And then this function here is a parabola that opens downward and has been shifted down by 1 on the y-axis. So it's going to look something like this. And where that would be 1, right? So this is what these look like, and what we're asking is what is the area in between these curves between 0 and 1. So I'm asking for this space. So the way that we're going to approach this situation is we're going to first take a look at this function, this linear function, which is negative x plus 3, and we're going to ask for the area under that curve between 0 and 1. And that's going to give us this area, and it'll be a positive value. But when we ask for the area between this curve and the x-axis, and we take the integral of that function between 0 and 1, we are going to get this value here. However, it's going to be negative. So we have to remember that we're going to get a negative value from that, but that's not going to matter because we're asking for this combined area. So essentially what we're going to do here is we're going to take the integral between 0 and 1 of negative x plus 3 dx. That'll be positive. And we're going to add that to the absolute value of the integral between 0 and 1 of negative 2x squared minus 1 dx. We're going to get a positive result. We just want area here. We want the exact area of that space. All right, so we could handle this a number of ways. We could turn this into one integral, or we could do these separately here. But let's go ahead and do these separately because it's going to make the most sense when we see this example. So this first integral here is going to be a pretty simple one. This is just going to be the reverse power rule. So x squared, but it's a negative 1/2 x squared plus 3x evaluated from 0 to 1. And we're going to add that to the absolute value of this will be x to the third, but it's going to be a negative 2/3 x to the third minus x evaluated from 0 to 1. So now we can evaluate these here. So this is going to be negative 1/2 times 1 squared plus 3 times 1 minus negative 1/2 times 0 squared plus 3 times 0. Let me pause. All right, so this is going to actually work out pretty nicely. We're going to end up with let's see, we have a negative 1/2 here plus 3. All right, this is all just 0. And then we have plus the absolute value of negative 2/3 minus 1. And this is, again, just 0. So if I want to get a common denominator on the left, this is going to be 5/2 plus the absolute value of negative 5/3 if I get a common denominator there. So this is the same as 5/2 plus 5/3. And that's going to equal 25/6. All right, so the reason that works out so nicely is that, well, and I say nicely, but we didn't have to do anything tricky because these functions didn't intersect within this window. And we could prove that if we wanted to check real quickly at the beginning, we could say, all right, well, let's make sure that negative 2x squared minus 1 doesn't equal negative x plus 3 within this domain, because if it does, we're going to have to do some different things here. As it turns out, these two functions are never equal, so you don't have to worry about this. But the next example is going to show us a situation where this is actually the case. All right, so we've got two pretty basic trig functions here, and we want the area between these two curves over the specified interval there. We have a general idea of what these functions look like if you graph them, and I'm just going to sketch them real quickly. I guess I'll try to use blue to keep the consistency with the last example. So 1, -1, I'm just going to sketch my sine curve there. All right, so that's sine if that is pi. And then I'm going to sketch cosine. This is going to be just a little bit more careful I have to be here. It's negative cosine, so not perfect, but pretty close. And we really don't even care about anything that's going on over here. So we're focused right there between pi over 2, which would be right there, and pi, which is right here. So this is the window that we're focusing on. Just from a rough sketch of this function, I can tell that the area I'm looking for is this area here, because that's between the two curves, and this area here, because that's between the two curves. But we've got something interesting going on here. There is a point where the function that's on top switches. So it's not just as simple as saying take sine of x and then subtract cosine of x, because that's going to work here, but over here I need to take cosine of x and subtract sine of x. So first of all, I need to figure out where it is that these two functions are switching. Where is the point that these functions are equal? So really quickly, when are sine of x and negative cosine of x equal to each other? And we know that this actually happens from the unit circle when x is equal to 3 pi over 4 or 7 pi over 4, and we could keep going here because obviously the unit circle is infinite, but the one we care about here is 3 pi over 4 because that's the one that happens between pi over 2 and pi. So I don't need to worry about 7 pi over 4 because that's this point here, right? And there would be infinitely many more of these if I continued in either direction, but I'm trying to figure out where that point is. So what I'm going to do is separate this into two separate integrals. My first integral is going to deal with this portion, finding that area, and then my second integral is going to deal with finding that area. So I've got an integral that goes from pi over 2 to 3 pi over 4. And in that situation, the sine function is the greater function. So what I'm going to do is subtract the value of sine of x minus the area under the curve of negative cosine of x. So what I'm doing in calculating this integral, and let me just package this up and show you where it is that I'm looking here, that's going to get me this space there. There's a better way to write this integral, right? We know from the properties of integrals that we can rewrite this in a much better way, a much clearer way as one integral. So I'm going to do that. And now let's think about this other section here. I also need this area to be added to that other area, and the way that I'm going to find that is just by doing the exact reverse. This time I have the cosine function on top, or the negative cosine function on top, and I'm going to be subtracting the sine function. And so that's going to give me this space here, and now I'm going to rewrite that. And remember, once I have that value, I'm going to want to add those two areas together. So now I've created an equation that I can actually solve. One thing I want you to notice is that the boundaries of that second integral are different because in this case we're going from 3 pi over 4 to pi. So I'm going to evaluate these and add them together, and just in the interest of keeping the video short, I'm going to go through this pretty quickly. If I factor the negatives out of this second integral, I can move the negative outside the integral, and it turns out that these are the exact same function then, so their antiderivatives will be exactly the same. Taking the antiderivatives here, hopefully you're noticing that this is the exact same thing as this. I probably should rewrite this, and I think I will in my next step here. Alright, I've plugged in the values, and now we can evaluate here. So sine of 3 pi over 4, we know that to be radical 2 over 2 from the unit circle, and so is cosine. But remember that cosine is going to be negative, so we're going to change that sign there. Minus a sine of pi over 2. And that's going to be 1 minus cosine of pi over 2, which is 0. So that takes care of the left side here, minus sine of pi. So that's 0 minus cosine of pi, negative 1. All right. And we probably could just write that if we want to be consistent here. It's plus 1. Okay. Minus sine of 3 pi over 4, we've already established that that is radical 2 over 2. And cosine of 3 pi over 4, we've already established is negative radical 2 over 2, so that sign is going to change. All right, so we've got this here. Obviously that there, just to be clear so you can see where all these components are coming from. All right, and finally, let's drop these brackets. So I have radical 2 minus 1 plus radical 2, and that's going to equal 2 radical 2 minus 2. And that turns out to be this area here.